Hello and welcome to yet another video of Cornerstones of Math. In this video, I'd like to talk about the problems from this year's entrance exam to Chennai Mathematical Institute, a distinguished higher education and research institute in India specializing in physics, math, and computer science. The Bachelor of Science or undergraduate entrance exam is divided into two parts. Part A consists of moderately difficult problems. Part B consists of 6 very difficult problems and are graded only if students meet certain criteria in Part A. One of my viewers suggested that I make an explainer video on these 6 problems in Part B, and upon examination I found that the problems are indeed extremely difficult yet also quite interesting conceptually. So let's dive into those 6 problems. Here's problem B1, the first problem from Part B. Suppose 5 complex numbers z1, z2, z3, z4, and z5 form the vertices of a regular pentagon that is inscribed in a circle of radius 2 with center at C that is 6 plus 8i. Problem A, find all possible values of S defined as z1 square plus z2 square plus z3 square plus z4 square plus z5 squared. State a value of z1 maximizing the absolute value of S. And problem B, find all possible values of P defined as z1, z2, z3, z4, z5. State a value of z1 minimizing absolute value of P. Alright, from the expressions for S and P, it is clear that we need to use the relation between roots and coefficients, also known as Vieta's formulas. That is, first, we must find the polynomial equation having z1, z2, z3, z4, and z5 as its roots, and then we apply Vieta's formulas on that equation to obtain the expressions for S and P. So, what kind of equation do z1, z2, z3, z4, z5 satisfy? Well, the most important clue is that these 5 roots form a regular pentagon inscribed in a circle as shown in the figure. And when it comes to the regular polygon inscribed in a circle, there's this famous property that is usually taught in basic complex analysis courses. On the complex plane, the n roots of the binomial equation z to the nth power equals 1 form the vertices of a regular n-gon inscribed in a unit circle centered at the origin with one of the vertices at 1. And the n roots are given as z equals cosine 2k pi over n plus I sine 2k pi over n, or e to the power of 2k pi over n times I as an exponential expression, where k can have values 0, 1, 2, so on up to n minus 1, or you can use from 1 to n, they are the same. But in our problem, the circle is not centered at the origin, but at a complex number c that is 6 plus 8i. In order to make the circle centered at the origin, we move this complex number c to the origin and move other points accordingly, which can be done by subtracting c from every complex number in the figure. Then we can find out that complex numbers z1 minus c, z2 minus c, z3 minus c, z4 minus c, and z5 minus c are on a circle of radius 2 with its center at the origin. Next, we are dealing with 2 problems at the same time. We want to shrink the radius of circle to 1, and we also want to rotate the pentagon so that one of the vertices is moved to the real axis. This is where the following property regarding the complex division comes in handy. For 2 complex numbers having arguments θ1 and θ2 respectively, when we do the division z1 over z2, we perform normal divisions like real numbers with their absolute values, but we do subtraction with their arguments. So back to the previous setting. Suppose that z1 minus c has an argument of theta, so that z1 minus c can be expressed as 2 times cosine theta plus I sine theta, or 2 times e to the power of I theta. Then, if we divide everything by z1 minus c, 2 things happen. First, the radius of the circumcircle of the regular pentagon shrinks to 1 because we divide by the absolute value of z1 minus c, which is 2. Also, the points rotate so that the point corresponding to z1 minus c moves to the real axis and hence becomes 1, because we subtract the argument of z1 minus c, which is theta. Therefore, we find out that 5 complex numbers, z1 minus c over z1 minus c, z2 minus c over z1 minus c, up to z5 minus c over z1 minus c, are on the unit circle with its center at the origin. Therefore, applying our knowledge on the roots of a binomial equation, z1 minus c over z1 minus c, z2 minus c over z1 minus c, z5 minus c over z1 minus c are roots of the equation z to the 5th power equals 1. We can say this in another way. We can say that z1, z2, so on z5 are roots of the equation z minus c divided by z1 minus c to the 5th power equals 1, which can be also written as z minus c to the 5th power minus z1 minus c to the 5th power equals 0, or using the exponential function, z minus c to the 5th power minus 32 times e to the power of 5I theta equals 0, because z1 minus c can be also written as 2 times e to the power of I theta. And because the roots of this equation are z1, z2, z3, z4, and z5, the left-hand side of the above equation must equal to z minus z1 times z minus z2 times z minus z3 times z minus z4 times z minus z5. And now it's time for Vieta's formulas. In order to compare coefficients, we expand both the left-hand side and the right-hand side. We don't expand z1 minus c to the power of 5 because it is a constant term of the polynomial. Meanwhile, we expand z minus c to the 5th power using the binomial theorem. This gives the left-hand side z to the power of 5 minus 5z to the power of 4 times c plus 10z cubed c squared minus 10z squared c cubed plus 5z c to the 4th power minus c to the 5th power, and this constant term minus z1 minus c to the 5th power. Expanding the right-hand side may seem exhausting, but many of you might already know the method. First, we have z to the 5th power. Then we have minus the sum of z1, z2, z3, z4, z5 times z to the 4th power. Then plus the sum of all possible products of two roots. There are 10 possible combinations times z cubed. Then minus the sum of all possible products of 3 roots times z squared, then plus the sum of the products of 4 roots times z, and then finally minus the product of all 5 roots. You can save space by writing in sigma notation. And this is the ultimate relation that we are going to use to solve this problem. So now we actually dive into problem A, and in the first problem we are asked to find possible values of the sum of squares of all roots, but none of the coefficients on the right hand side contains the sum of squares of the roots. Notice that the coefficient of z cubed only contains the products of 2 different roots, since indices j and k cannot have the same value. However, we can use the expansion of the square of the sum of 5 roots, which definitely gives the sum of squares of those roots. The remaining part is the sum of the products of 2 different roots twice. Therefore, S, the sum of the squares of the roots, can be expressed as sum of the roots squared minus 2 times the sum of products of 2 different roots. And if we compare the coefficients, the sum of the roots is 5 times c, and the sum of the products of 2 different roots is 10 times c squared. So we have 5c squared minus 2 times 10c squared, which gives the result 5c squared, or 5 times 6 plus 8i squared. Notice that s has a constant value, independent of the position of z1. This means that any point given on the circle as z1 gives the same maximum value of absolute value of s, which is 5 times absolute value of c squared, hence 500. This value never changes even if the position of z1 on the circle changes. Next, problem B. Finding possible values of p that is the product of all 5 roots. Using our result of Vieta's formulas again, the product of all 5 roots appears at the constant term on the right-hand side, and the constant term on the left-hand side is this. So we can find out that p is equal to c to the 5th power plus z1 minus c to the 5th power, or equivalently c to the 5th power plus 32 times e to the power of 5I theta. Here, z1 moves on a circle, absolute value of z minus c equals 2. So you can say that p can have values of c to the 5th power plus z1 minus c to the 5th power when z1 is on the circle absolute value of z minus c equals 2, or equivalently, values of c to the 5th power plus 32 times e to the power of 5I theta as real number theta changes, which implies the aforementioned circle condition. But can we provide more geometrical interpretation for the values of p? Well, since z1 is on the circle absolute value of z minus c equals 2, we have absolute value of z1 minus c to the 5th power is equal to 2 to the 5th power, hence 32. Using this, we can obtain absolute value of p minus c to the 5th power is equal to absolute value of z1 minus c to the 5th power, which is 32. Which is also the equation of the circle. That is, p moves on a circle centered at c to the 5th power, hence 6 plus 8i to the 5th power, and having the radius of 32. Let us now consider the minimum value of absolute value of p. Absolute value of p is the distance to the point corresponding to p from the origin. And we know that this distance is minimized when p is located at the nearer intersection point where the ray passing through the center of the circle meets the circle itself. Therefore, the minimum value is distance to the center of the circle, absolute value of c to the 5th power, minus the radius 32, which gives 10 to the 5th power minus 32, hence 99,968. What would be the condition on z1 when absolute value of p becomes minimum? In order to answer that question, let us get back to our initial circle showing 5 roots centered at c. Let alpha be the argument of c. You can easily find out that alpha is equal to the inverse tangent of 3/4. Then the argument of c to the 5th power is 5 alpha. We are trying to find all possible cases, so we can express the angle between this ray and the real axis as the general angle 5 alpha plus 2k pi, where k is integer. If p is located at the position of minimum magnitude, then if we move it by the translation which brings c to the 5th power to the origin, point p will move to point p minus c to the 5th power, and because this point is in the opposite direction to the initial ray, its argument must be 5 alpha plus 2k pi plus pi. So we have argument of p minus c to the 5th power is 5 alpha plus 2k pi plus pi, and we have already found that p minus c to the 5th power is given as z1 minus c to the 5th power, or 35 times e to the power of 5I theta, meaning that argument of p minus c to the 5th power must be 5 times the argument of z1 minus c, hence 5 theta. Therefore, the above condition becomes 5 theta is equal to 5 alpha plus 2k plus 1 times pi, which gives the condition 5 times theta minus alpha is equal to 2k plus 1 times pi. So the minimum occurs when 5 times the difference between theta and alpha are odd multiples of pi. The second problem can be solved by another method using the triangle inequality. This method is also presented in the official solutions, so I'll briefly explain here. We will use the previously obtained result, which is that p is equal to c to the 5th power plus z1 minus c to the 5th power, or c to the 5th power plus 32 times e to the power of 5i theta, where z1 is located on a circle, absolute value of z minus c equals 2. When dealing with minimum value of absolute value of p, we have to use the less famous triangle inequality regarding the difference between two quantities, also known as the reverse triangle inequality. We also have to consider the equality condition here, but you must also be aware that the equality conditions for left and right inequalities are different. If you have hard times understanding the complex number version of the inequality, just think of it being analogous to the vector version, which can be geometrically understood. So with this inequality in mind, the absolute value of p, which is the absolute value of this expression, is greater than or equal to absolute value of c to the 5th power minus absolute value of z1 minus c to the 5th power. Hence, it is difference between 10 to the 5th power and 32, which is 99,968. The equality condition is that c to the 5th power and z1 minus c to the 5th power are in the opposite direction, meaning that the difference between argument of c to the 5th power and argument of z1 minus c to the 5th power is equal to odd number multiples of pi. So using these arguments, we have 5 alpha minus 5 theta equals 2k plus 1 times pi, so we arrive at the same condition we obtained before. Next, problem B2. Consider the following functions from the coordinate plane to itself. Let R alpha be counterclockwise rotation by angle alpha, and let F alpha be reflection in the line that makes counterclockwise angle alpha with the x-axis. For example, r 90 degrees of 1, 0 is the rotation of 1, 0 counterclockwise by angle 90 degrees, hence it gives 0, 1. And f 90 degrees of 1, 0 means that the reflection of the line then makes 90 degree angle to the x-axis, hence basically reflection over the y-axis, so it gives negative 1, 0. We have 3 problems A, B, and C, and let's take a look at them one by one. Problem A. Evaluate R alpha of the point R cosine theta, R sine theta, and F alpha of the point R cosine theta, R sine theta, where R is a non-negative real number and theta is any angle. Let's deal with the rotation case first. Let Q, which is R cosine theta, R sine theta, be the initial point, which is at distance r from the origin and angle theta to the positive x direction, and let Q prime be the rotated point. Both rotation and reflection preserve the distance from the origin, hence we only need to focus on angle changes. Notice that the rotated point Q prime forms an angle theta plus alpha to the positive x direction, so we know that the rotated point is r cosine theta plus alpha, r sine theta plus alpha. Next, the reflection. Similarly, let Q be the initial point r cosine theta, r sine theta, and Q prime be the reflected point. The red line in the figure is the line of symmetry. Notice that the line of symmetry and line OQ forms angle alpha minus theta. Hence, the angle between the line of symmetry and line OQ prime is also alpha minus theta. Therefore, the angle between OQ prime and the positive direction of x-axis is theta plus twice the alpha minus theta, which is equal to 2 alpha minus theta. Therefore, the reflected point is r cosine 2 alpha minus theta, r sine 2 alpha minus theta. And problem B, geometrically describe the composition of functions f alpha of f0. Note that f0 is the reflection in the x-axis. I will show you 2 methods, and let's start with the most intuitive method, which is just using the results we obtained in the previous problem. Consider a general point which can be expressed as r cosine theta, r sine theta. We have to do the f0 operation first, which is the reflection in the x-axis. Let's use the fact that the reflection in the x-axis changes the sign of the y-coordinate while leaving the sign of the x-coordinate unchanged. Hence we obtain r cosine theta, minus r sine theta. This can be also written as r cosine minus theta, r sine minus theta, which is the general expression of a point using positive distances from the origin. Now it's time to perform f alpha operation on this point. The operation changes the angle to 2 alpha minus the initial angle, hence we have 2 alpha minus theta as the angle, which can be written as r cosine theta plus 2 alpha, r sine theta plus 2 alpha. And this is the same format as the rotated point, with initial angle theta plus rotated angle. But now we have 2 alpha here, so it is equal to r2 alpha of the point r cosine theta, r sine theta. This means that the function composition f alpha of f0 is equal to rotation function r2 alpha. As for the second method, this problem is still not that hard to do using pure geometry. Let's use this initial setup with initial point Q with line OQ forming angle theta to the horizontal line. First, we need to do the reflection in the horizontal line. This will generate point Q prime, and the line OQ prime and the horizontal line will also form an angle theta. Next, we perform a reflection on this point Q prime, now over the red line of symmetry, to generate a new point Q double prime. Notice that the angle between the line of symmetry and OQ prime is alpha plus theta. Hence, the angle between the line of symmetry and line OQ double prime also has to be alpha plus theta. Finally, we investigate the angle relation between line OQ double prime and the initial line OQ. The initial line OQ forms an angle alpha minus theta to the line of symmetry. Hence, two lines OQ and OQ double prime form an angle alpha minus theta plus theta, which is equal to 2 alpha. So we obtain the same result. And the final problem C, for any angles alpha and beta, and I really love the phrase here, geometrically describe function composition f alpha of f beta in one crisp sentence. You'll find out soon that the answer is indeed simple and beautiful. Of course, I'm going to do it the similar way as in problem B. And we have next part of the problem, which is that we have to find g of p, where function g is f 20 degrees after f 25 degrees 9 times, and P is the point 20, 25. Alright, so the first part, in a similar manner to the previous problem. So for a general point r cosine theta, r sine theta, we have to do f beta first, which gives the point r cosine 2 beta minus theta, r sine 2 beta minus theta. Then we have to do f alpha on that point. So now the angle changes to 2 alpha minus the previous angle. So now we have the angle 2 alpha minus 2 beta minus theta, which can be written as theta plus 2 times alpha minus beta. And again, this is in the same form as rotation, now with rotated angle 2 times alpha minus beta. Therefore, f alpha of f beta is equal to r2 times alpha minus beta. That is, two consecutive reflection operations are equivalent to a rotation operation. Using this result, let us deal with the next part of the problem, finding the point g of p. G is the function composition f 20 degrees after f 25 degrees 9 times, And notice that f 20 degrees of f 25 degrees is equal to the rotation operation by the angle 2 times 20 degrees minus 25 degrees. Hence, it is rotation by the angle negative 10 degrees, or 10 degrees in a clockwise direction. Therefore, function g, which is this 9 times, is just rotation by negative 10 degrees 9 times, and rotating negative 10 degrees 9 times is just equal to rotation by negative 90 degrees. So function g is just a simple clockwise 90-degree rotation. Applying this to our given point P, that is 20, 25, we have to rotate this point 90 degrees clockwise, which is very simple and even can be found by simple geometry, which gives the final point 25, negative 20. Problem B3. A particle starts at 0, 0 and travels in the first quadrant along a straight line. It maintains the slope and stays in the square bounded by the lines x equals 0, x equals 1, y equals 0, and y equals 1 as follows. Whenever it reaches the boundary of this square, it magically jumps 1 unit to the left or down or both as applicable. In other words, for a that is less than 1, it jumps to a, 0 upon reaching a, 1. It jumps to 0, a upon reaching 1, a, and it jumps to 0, 0 if it reaches 1, 1. In a graphical representation, the particle jumps like this when it reaches the boundary. If the particle ever reaches a previously visited point, it stops. For example, starting from 0, 0, a particle can travel to 1/2, 1, then it must jump to 1/2, 0, and by the same slope it reaches 1, 1, then it must jump to 0, 0 and stops. This is a trajectory of length square root of 5. So as a graphical representation, the particle's trajectory looks like this, excluding the jump. Another way to visualize this trajectory is to let the particle continue across the boundary y equals 1 and interpret what happens. In this way, the particle's trajectory given in the example will look like this. We will use this second type of visualization whenever it feels appropriate. Now we have 3 problems A, B, and C, and let's take a look at them one by one. Problem A. What are all the possible stopping points for finite trajectories? Well, this is the type of problem where you have to make an educated guess, which requires some experience in playing by the rules given in the problem. That kind of thought process is omitted in this video, but after trying many cases, some of you might reach the following conclusion. Perhaps only the starting point 0, 0 can be the stopping point. Let's prove this by proof by contradiction method. We have already seen the case where 0, 0 can be the stopping point, so all we have to do is to prove that any points other than 0, 0 cannot be the stopping point. In that sense, let us assume that there exists another stopping point P, Q, which is not the origin. Then there must also exist at least one slope S leading to that stopping point. Because there can exist only one line that passes the given point with the given slope, the particle's trajectory originating from 0, 0 and terminating at P, Q is uniquely determined if those two pieces of information are given. Now, P, Q being the stopping point means that the particle visits this point twice. But because the particle can reach this point only by a unique trajectory given the slope, this means that the particle also visits other points on the trajectory, like point P', Q' in the figure, twice. But according to the rules given in the problem, the particle must stop if it visits the same point twice, meaning that it must stop at points like P', Q', which is before reaching point P, Q. But we have already assumed that particle can travel all the way up to P, Q, which is a contradiction. Therefore, our assumption that P, Q can be the stopping point is wrong, meaning that only 0, 0 can be the stopping point. Problem B. If the particle starts at angle 30 degrees with respect to the x-axis, show that it never stops. From now on, I think it is convenient to use the alternative representation of the trajectory, which is that we extend the trajectory beyond the initially given boundaries. In that case, the particle traveling a finite trajectory and eventually reaching the only possible stopping point 0, 0 can be represented as the particle reaching the lattice point on the coordinate plane, i.e. reaching the point having integer coordinates. For example, the particle reaches the lattice point 1, 2 if the slope is 2. In our case, the slope of the trajectory is tangent 30 degrees, hence 1 over square root of 3. We are going to use the proof by contradiction again, meaning that we assume that the trajectory with slope 1 over square root of 3 stops at some lattice point m, n, where m and n are integers. This means that n over m is equal to the slope 1 over square root of 3, or equivalently, m over n is equal to square root of 3. Notice that the left-hand side is rational and the right-hand side is irrational, hence the contradiction. Therefore, the particle never stops. And the problem C, find the two smallest possible integer length among all finite trajectories. We continue using the alternative representation of the trajectory, where the particle having the finite trajectory can be demonstrated as the trajectory reaching the lattice point, the point with integer coordinates. If the trajectory ends at the lattice point a, b, where a and b are of course integers, its length c is given as the length of the hypotenuse of a right triangle having a and b as its other two side lengths. And we want this c to be an integer. Some of you may also know the fancy equivalence statement, which is that a, b, and c must be the Pythagorean triple. The smallest case is a very famous one, giving the hypotenuse length of 5 in a 3, 4, 5 right triangle. A bit of a caution though, some of you may also know that 6, 8, 10 triangle also give the integer hypotenuse, but this case does not count here because if you draw the trajectory over the unit squares, you'll notice that the trajectory meets the lattice point 3, 4, thus terminates there before reaching 6, 8. This happens because 6 and 8 have a common divisor 2. Therefore, if we want a, b to be the legit terminating point, we need additional condition that a and b are co-prime. Under this additional condition, the next smaller integer value of c is 13, which comes from the 5, 12, 13 triangle. The problem before is about the functions satisfying special property. The domain of function f is the set of positive integers, and f of xy is equal to f of x plus f of y for all x and y. Answer the independent questions below, where independent means data from problem A are not valid for the rest. Also, we may have to use the prime factorization of 2025. So we have 3 questions in total, and the first question says, suppose f of 2025 equals 0, f of 20 equals 10, and f of 25 equals 20. What is the smallest n for which f of n is not uniquely determined? Write values of f of x for each positive integer x that is less than n. Obviously, we need to smartly play with this rule. F of xy is equal to f of x plus f of y. As a starter, let's try to find the value of f of 1. Substituting both x and y with 1, we get f of 1 equals f of 1 plus f of 1, so we obtain f of 1 equals 0. Perhaps the next easiest step is using the given value of f of 25, because 25 is equal to 5 squared, so f of 25 can be split into f of 5 plus f of 5, so we have 20 equals 2 times f of 5, giving f of 5 equals 10. Next, let's use the given value of f of 20. Since 20 equals 4 times 5, so f of 20 splits into f of 4 plus f of 5. So using the given values, 10 equals f of 4 plus 10, giving f of 4 equals 0. Also, notice that since 4 is 2 times 2, f of 4 equals 2 times f of 2. so we can also obtain f of 2 equals 0. Finally, let's use the given value of f of 2025 and also its prime factorization. Using this, we can easily find out that f of 2025 can be split into f of 81 plus f of 25. So using the previously obtained values, 0 equals f of 81 plus 20, giving f of 81 equals negative 20. Here, f of 81, which is negative 20, is equal to 2 times f of 9. And since f of 9 can be split into 2 times f of 3, we have 4 times f of 3. This gives f of 3 equals negative 5. And using values of f2 and f of 3, we can obtain values of f of 6, which is also negative 5. So far, we have obtained every value from f of 1 to f of 6. As for the value of f of 7 though, notice that none of the elements given as the input of the function contains 7 as a divisor. This means that f of 7 can have arbitrary values. Hence, the minimum value of n where f of n is not uniquely determined is 7. Let's move on to problem B. Is there a such function f for which f of x equals 0 for all positive integer x that is less than 2025 to the power of 2025, but f is not identically 0? Show how to define such f or show that it is not possible. So, can such a function f exist? Well, the answer is yes. And in order to provide an example, let us try to understand at which input values does the function f of x become 0. The function must be 0 for all values of x below 2025 to the power of 2025. So the only way to avoid f of x being identically 0 is that for some number p that is above or actually above or equal to 2025 to the power of 2025, we define f of p as a non-zero value. But we must not be so quick to assume that such number p exists, because a lot of number on the right side can also give 0 as the value of the function. For example, if we pick two natural numbers n1 and n2 such that both n1 and n2 are less than 2025 to the power of 2025, but their product n1 and 2 is greater than or equal to 2025 to the power of 2025, the rule suggests that f of n1 and 2 becomes 0, even though n1 and 2 is above 2025 to the power of 2025. Therefore, if you want to make sure that p is not expressed by any of the products of number below this number, we must choose the value of p in a way that p is not divisible by any of the natural numbers below 2025 to the power of 2025. Luckily, we can guarantee that such number p does exist. Look at the property that p must satisfy. It reminds you of prime numbers, right? If p is a prime number on the right side of the number line, then that prime number p automatically satisfies the aforementioned property. Therefore, knowing that such p exists, we can define function f of x as 0 for all numbers x that is below 2025 to the power of 2025, and for at least one prime number p that is greater than or equal to 2025 to the power of 2025, we define the value of f of p as some non-zero number c. In problem C, the domain of a function g is the set of positive rational numbers, codomain is the set of integers, and g of xy equals g of x plus g of y for all positive rational number x and y. Suppose g of a equals 24, g of b equals 2025, and g of c equals 10 to the power of 2025 for some rational numbers a, b, and c. Show that there are infinitely many rational numbers r such that g of r equals 1. This problem is solved in multiple steps. First, let us prove that such rational number r exists. But before we get to that part, let us briefly summarize some important properties of function g satisfying this important rule. G of xy equals g of x plus g of y. The obvious one is that g of 1 is equal to 0, which can be obtained by letting x and y as 1. As for the next property, notice that g of x squared gives 2 times g of x, and using this, g of x cubed is equal to 3 times g of x, and g of x to the 4th power equals 4 times g of x, and so on. So we obtain that g of x to the nth power equals n times g of x for all natural numbers n. Next, for rational number x that is non-zero, let us consider g of 1 over x. We can deal with this by adding g of x, because then it gives g of 1 which equals 0. This means that g of 1 over x is equal to minus g of x. And if you think about it, this makes the second property true for all integers n. Now, if you think that these properties are all very similar to the properties of logarithms, then well, you have keen eyes. Although function g and also function f from previous problems are not exactly the most familiar type of logarithmic function, because their domains are more restricted compared to usual positive real numbers, they still exhibit the core properties of logarithmic functions, and realizing this logarithmic nature of the function might help you save time in some calculation parts. The next important property or lemma required to prove the existence of R is the famous Bezoos identity, which states the relation between two or more integers and their greatest common divisor. The box shows Bezoos identity for 2 integers, but Bezoos identity also applies to 3 or more integers, like our given problem. Let's take a look at 3 specific given values of function g. What can we do with those? Well, we were taking a look at Bezoos identity, so it feels natural to investigate the greatest common divisor of these 3 numbers. And if you take a look at their prime factorizations, it is not difficult to find out that the greatest common divisor is 1. Therefore, there exist integers x, y, and z satisfying 1, the greatest common divisor, is equal to 24 times x plus 2025 times y plus 10 to the power of 2025 times z. Here we can substitute numbers with g of a, g of b, and g of c, and this entire thing is equal to g of a to the power of x times b to the power of y times c to the power of z because of the logarithmic nature of the function g. Therefore, if we take r as this a to the power of x times b to the power of y times c to the power of z, then r is definitely a positive rational number, and we have g of r equals 1, hence the existence is proved. Next, let us prove that there are infinitely many such rational numbers R. Infinitely many positive rational numbers actually, because of the domain condition. Here, if you cannot figure out how to approach this problem, let us just assume that the given proposition is true and see what happens then. So what if this is true? What would happen if there are infinitely many rational numbers R1, R2, R3, and so on, satisfying g of R1, g of R2, g of R3, and so on, all equal to 1? Well, one thing we can do is that we can define S by choosing any 2 different R values and calculating the ratio between them. Alright, so this is a simple definition, but why do we care about the ratio? Well, the significance of this S is that first, S is a positive rational number not equal to 1, and second, g of S is equal to g of Ri minus g of Rj, so it gives the value 0. That is, we have the following equivalent statement. We can find a positive rational number S such that S is not equal to 1 and g of S equals 0. Actually, we cannot call this an equivalent statement yet because we have only proved one direction so far, and we are still required to prove the other direction as well. So what if this is true? What if we can find a rational number S that is not equal to 1, satisfying g of S equals 0? Well, in the previous step, we proved that there exists at least one rational number, let's call it R prime, satisfying g of R prime equals 1, namely this value. Now using this r prime and s, we can find out that for infinitely many integers k, g of r prime times s to the power of k gives the value 1. Therefore, if we think of this r prime s to the power of k as new r, then it is guaranteed that there exist infinitely many rational numbers r such that g of r equals 1. So with this equivalent relation established, let's see if we can find such rational number s, whatever the range of function g might be. It can be done by following clever definition. Let us choose two different prime numbers p and q. Here, let me emphasize that g of p and g of q are both integers because it is stated in the problem that the codomain is the set of integers. Then, let us define s as p to the power of g of q divided by q to the power of g of p and see what happens. We need additional condition though, which is that at least one of g of p and g of q is non-zero. In other words, suppose that we can choose two different prime numbers p and q in a way that not both g of p and g of q are 0. Then you can easily notice that s is a positive rational number that is not equal to 1. And most importantly, you can find out that the value of g of s, which is the value of this, equals 0, which fits our condition in the equivalence statement. But sadly, this does not cover all possible cases of function g. What if such condition, at least one of g of p and g of q is non-zero, is not satisfied? That is, what if the range of function g is given in a way that g of p is equal to 0 for all prime numbers p? This makes the value of this expression 1, which is invalid value for s. Well, in that case, we just let s be any prime numbers p. Then you can easily notice that the conditions in the equivalence statement are satisfied. Therefore, we can always find the appropriate rational number s, whatever the values of function g may be. Hence, the infinitude of r is also proved. And this concludes the entire problem C. Problem B5. Solve the following two problems A and B. Part B can be done independently and may be easier, even though I think, well, not really. And let's actually read those problems here. For problem A, construct a function f with domain being the set of real numbers such that f is differentiable, weakly increasing, meaning that if b is greater than a, then fb is greater than or equal to fa, bounded, meaning that all values of function f of x is sandwiched between some two values small m and capital M, and the limit of the derivative f prime x as x approaches infinity does not exist. The hint suggests that we should consider the derivative function f prime of x first. And for problem B, construct a function g with domain being the set of real numbers such that g is differentiable, strictly increasing, meaning that if b is greater than a, then g of b is strictly greater than g of a, bounded. Now limit of the g of x as x approaches negative infinity equals 0, and limit of the derivative g prime of x as x approaches infinity, and limit of the derivative g prime x as x approaches negative infinity, both do not exist. And the hint suggests that try to use function f obtained in part A and modify that function a little bit. Alright, so problem A, finding function f that is differentiable, weakly increasing, bounded, and the limit of the derivative at infinity does not exist. Just like the hint suggests, let us deduce some conditions that the derivative f prime of x should satisfy using the restrictions given in the problem. First, what can be inferred from the fact that f is differentiable? Well, we can infer that the derivative f prime of x is defined and continuous everywhere. Next, what about f being a weakly increasing function? Well, then we know that the derivative f prime of x is greater than or equal to 0 for all real numbers x. Next, the fact that f is bounded. To relate this property with derivative, we should recall that the original function f of x and its derivative are related not only by differentiation, but also by integration if you think of it in the reverse direction. And by integral, it means the area under the function f prime of x. This area being bounded means that the integral of the derivative on the entire domain must have some finite value. So we have the integral of the derivatives at entire domain is finite. Finally, let us consider the fact that limit of the derivative f prime x as x approaches infinity does not exist. So we have a diverging limit for the non-negative derivative. One way such limit can diverge is the limit approaching infinity. However, this immediately leads to the problem that the area under the curve cannot have finite value, hence this is an invalid case. Another way that the limit can diverge is that derivative f prime of x oscillates indefinitely between two finite values. In this case, the limit at infinity also does not exist because the function never approaches the single value. But this does not automatically guarantee the finite area condition. Even for the example in the figure, where the lower bound is the lowest possible value 0, we still add up some areas, actually infinitely many chunks of areas when we are integrating all the way up to infinity. So how can the area obtained by infinitely adding up something leads up to a finite value? Well, one such example is geometric series, right? I mean, if you take a look at this simple geometric series, it consists of infinitely many terms, but it gives you the finite value as its sum. So we are going to construct the derivative function f prime in a way that the areas being added up have the values of individual terms of a geometric series, which can be done as follows. We define derivative f prime x as a function that creates isosceles triangles, giving maximum values at x equals 1, 2, 3, and so on. The heights of all triangles are 1, hence the derivative oscillates between 0 and 1. Around x equals 1, the graph increases linearly, starting from x equals 1 minus 1/2, then peaks at x equals 1, and then decreases linearly, reaching 0 at x equals 1 plus 1/2. Around x equals 2, the triangle is constructed in the interval that spans 1 over 2 squared to the left and 1 over 2 squared to the right. And around x equals 3, now the interval 1 over 2 cubed to the left and 1 over 2 cubed to the right. So generally, around x equals n, we have a triangle of height 1 whose base spans 1 over 2 to the power of n to the left and 1 over 2 to the power of n to the right. When x is negative, the graph is just a mirror image of the positive x region. If you want mathematical expression for the derivative, we can express like this. Notice that this graph gives the areas of triangles 1/2, 1 over 2 squared, 1 over 2 cubed, and so on. Now, if we define f of x as the integral of this function that also has value 0 at x equals 0, then we have the graph that looks as follows. The function starts at 0, then it increases when x is from 1 minus 1 over 2 to 1 plus 1 over 2, and in this interval, the value of the function increases by 1/2. Then it stays constant for a bit, and then increasing again when x is from 2 minus 1 over 2 squared to 2 plus 1 over 2 squared, now by the amount of 1 over 2 squared. Then upon passing x equals 3, the function increases by 1 over 2 cubed, and generally upon passing through x equals n, the function increases by 1 over 2 to the power of n. Because the increased values form a geometric series, the function is bounded between -1 and +1. Next, problem B, finding a function g that is differentiable, strictly increasing, bounded, limit at the negative infinity is 0, and the limit of the derivative at positive infinity and negative infinity do not exist. Of course, following the hint, we are going to use our previously obtained function f and construct g from f by making necessary adjustments. This function f has several problems which make it invalid to serve as function g. First, function f is only weakly increasing, not strictly increasing. Second, the limit at negative infinity is -1, which is non-zero, so we have to somehow adjust this limit. Now, what does strictly increasing mean in terms of derivatives? Well, function g of x being a strictly increasing function means that the derivative g prime of x is greater than or equal to 0, and x is where the derivative becomes exactly 0 only exists as separated points, or isolated points, or discrete points. This property can be pretty intuitively understood, so let's jump right onto the problem that our previously obtained derivative f prime of x possesses. You can see that f prime becomes 0 at many intervals, making this an invalid derivative for g prime. By the way, connecting all the given triangles like in the figure doesn't work. We add up the base length of these triangles, we obtain value 2, a finite value. In other words, the function constructed in this manner only has finite horizontal length, hence it cannot be extended all the way up to infinity. So we have to find another way, which I'm about to show you right now. As a first step, let us modify our given function f to make it strictly increasing. First, let us introduce a new function k of x that is strictly increasing and bounded. There are many examples of such k of x, including arctangent function, hyperbolic tangent function, error function, and with a little bit of work with the common exponential functions, etc. Then, if we add this to our previously obtained function f of x, the resulting function f of x plus k of x is strictly increasing because the derivative of k is always positive. Next, we need to adjust the value at negative infinity so that it satisfies the given condition that the limit of g of x at negative infinity becomes 0. This can be done as follows. Let us denote the limit values of f of x and k of x at negative infinity as capital F and capital K respectively. Then, if we define g of x as f of x plus k of x minus the sum of those limit values, then this g of x satisfies limit at the negative infinity equals 0. By the way, g of x defined in this way also satisfies the limit conditions of its derivative because f prime of x part of the derivative still oscillates, hence diverges. And finally, we have this ridiculously long problem B6. You don't have to read all of this right now, because I will show you each problems in bigger texts. First of all, we have some sort of rule part of the problem, so let's take a look at this part first. So here's the basic rule of the problem. A1, A2, A3, so on, An is a sequence of distinct numbers, each written on a card. Take the cards one by one in order. Place them into stacks subject to this rule. One can only place a smaller number on top of a larger number, or one can start a new stack with a card. Here is a simple greedy strategy. Make stacks along a line and place the incoming card on top of the leftmost stack possible. So if the incoming card cannot be placed on any existing stack, then we use that card to start a new stack to the right of all current stacks. For example, with the sequence 3, 7, 2, 5, 6, 4, 9, 8, we get this result of 4 stacks. If I may explain it in more detail, so we have this sequence. So obviously 3 goes into first stack, And as for the next term 7, it cannot be placed on top of 3, so it goes to next stack. And as for the next term 2, it can be placed on top of 3. And as for 5, it cannot be placed on top of 2, but it can be placed on top of 7, hence it goes to the second stack. And we go on and on. So 6 forms a new stack because it cannot be placed on top of 2 or 5. 4 goes to stack number 2. 9 forms a new stack. And 8 goes into stack number 4. Here's our first problem. A. Show that under the greedy strategy, the top numbers on the stacks increase from left to right. For example, in previous case we just examined, the top numbers are 2, 4, 6, 8, hence they are in increasing order. We will use mathematical induction for a proof. That is, given the sequence A1, A2, A3, AN, we are going to focus on how the entry AK plus 1 affects the stack when the stack of k numbers is already given. So our induction hypothesis would be this. K numbers A1, A2, AK are stacked in a way that the top numbers increase from left to right. Let us then examine the process of introducing AK plus 1 to this stack. There are two possibilities. Generally, AK plus 1 will skip over the stacks whose top numbers are less than AK plus 1 and eventually will be placed on top of some previous top number y that is greater than AK plus 1. This is represented in the figure where there are L stacks to the left of the stack containing AK plus 1 and y, and R stacks to the right of the stack containing AK plus 1 and y. We can use letter X to denote the top numbers on the left stacks and letter Z to denote the top numbers on the right stacks. Otherwise, that is, if all previous top numbers are less than AK plus 1, then AK plus 1 will simply form a new stack and become the first and top number in that new stack. Our induction hypothesis for k entries indicates that all top elements on the left L stacks are less than y, and all top elements on the right R stacks are greater than y. This also applies to case 2, where some parts of the inequality chain do not exist. Now, AK plus 1 being on top of y suggests that AK plus 1 is less than y, and AK plus 1 skipping over the previous top number XL suggests that AK plus 1 is greater than XL. Therefore, AK plus 1 is sandwiched between XL and y, or for case 2 where such y doesn't exist, just greater than XL. So now the stacks contain k plus 1 numbers, and if we compare the top numbers again, now including the new top number AK plus 1, you can easily notice that the increasing property of the top numbers is still preserved, and this concludes the proof. Problem B. Show that under the greedy strategy, the number of stacks is the length of a longest possible increasing subsequence of A1, A2, A3, AN. Here, a subsequence means sequence AI1, AI2, so on up to AIK with indices I1, I2, IK in an increasing order. The example given above has an increasing subsequence of length 4. For example, we have 3, 5, 6, 8, but this is not the only one, and you can find other increasing subsequences such as 3, 5, 6, 9, 2, 5, 6, 8, or 2, 5, 6, 9. However, none of the possible increasing subsequences can have length 5. So the maximum possible length is 4, and it also gives 4 stacks as claimed. And we are going to use the hint. For an entry x in the given sequence, define L of x as the length of a longest increasing subsequence whose last entry is x. What can we find if we examine the values of L of x in the example? Well, we are going to do exactly what the hint suggests, so let us try to fill in this table by finding the values of L of x for the entries x given in the example. There's not much to talk about the first entry because it is just length 1. As for next x, notice that the longest subsequence that ends with 7 is 3, 7. Hence the maximum length, hence the value of L of x becomes 2. However, as for x equals 2, the longest increasing subsequence that ends with 2 is just 2, so the value of function L becomes 1. As for 5, we have an increasing subsequence of length 2. And for 6, we have an increasing subsequence with length 3. And that length shrinks to 2 if it has to end with 4. And as for 9, the length becomes 4, and same goes for 8. So we have filled the table, but what is the significance of these values? Why does the problem want us to find values of L of x? I will just give you a more straightforward hint. Here's the picture of completed stacks. Can you find the relation between the values of Lx and the arrangement of numbers in completed stacks? Well, I cannot waste too much time on the video, so in case you haven't noticed, the values of Lx is equal to the stack number where entry x is placed, which I will denote as n of x. In the given example, the entries 3, 7, 2, 5, 6, 4, 9, 8 are stored in stacks 1, 2, 1, 2, 3, 2, 4, 4. This is just a guess at this point, but this guess just straight up proves the main point of the problem. So let us prove this guess. Two observations are critical for this proof. Observation 1. First, consider an entry x which is placed in stack nx. I will omit the trivial case in which n of x equals 1. Here, x being in stack n of x implies that x has to skip or jump over the previous stack, which is stack n of x minus 1. This happens when x encounters a number smaller than x in that stack. So we can say that there exists a number y in the previous stack, which appears earlier than x in the sequence, and also smaller than x, so x jumps over this number y. If I may explain again, first y enters the stack n of x minus 1. Then x enters the stacks, but it cannot be placed on top of y, hence it jumps over to the next stack. This means that there exists an increasing subsequence from y to x. That is, we can sort of connect y and x, and thereby stacks n of x minus 1 and n of x by some increasing subsequence. We can continue on with this process inductively, meaning that this knowledge can be extended to the entirety of stacks, all the way back to stack number 1. Therefore, we can say that there exists an increasing subsequence that ends at x and contains at least one entry from each stack. This means that L of x, the length of the longest increasing subsequence, must be greater than or equal to the number of stacks n of x. Now the equality seems intuitive, but how can L of x be greater than n of x? Well, such case is possible when the subsequence containing entries from adjacent stacks, for example y and x, contains a third term in the middle. This involves the subsequence that moves in a vertical direction within the same stack. But is such movement possible? That is our second observation. Can the increasing subsequence have vertical movements, like x to x1 or x to x2 in the figure? Let me explain. First, forming a subsequence in a downward direction is impossible, because x placed on top of x1 implies that x1 appears earlier than x in the sequence. Moreover, forming a subsequence in an upward direction is also impossible, because x2 placed on top of x implies that x2 is less than x. This means that this subsequence cannot be an increasing subsequence. Therefore, forming an increasing subsequence in either vertical direction is impossible. So in other words, any possible increasing subsequence cannot contain two or more terms from the same stack. This means that L of x, the length of the longest increasing subsequence, must be less than or equal to the number of stacks n of x. Here, L of x being strictly less than n of x case occurs when an increasing subsequence does not contain entries of every stack. We have already found out that such case is impossible from observation 1, but I'm just stating what can be inferred by this sentence alone. So combining our two observations, we finally have our guess proved, which is that the length of the longest increasing subsequence up to entry x is equal to the stack number where x is placed. The main goal of the problem is to show that the total number of stacks, which I will denote as capital N, is the length of a longest possible increasing subsequence. This is now obvious because the number of stacks is the rightmost stack number, which can be expressed using an entry x prime in that stack, and this equals L of x prime, which can be interpreted as the length of the longest increasing subsequence possible. Problem C. Show that the greedy strategy gives the minimum possible number of stacks. We have already done most of the work in the previous problem, so in here let me just quickly explain them in a more general setting. The total number of stacks, capital N, equals the stack number n of x prime, where x prime is an entry that belongs to the final stack. Here, let's recall observation number 2 from the previous problem, which states that the increasing subsequence cannot contain two or more terms from the same stack. Or equivalently, each term in the increasing subsequence belongs to a different stack. The thing is, this property applies to any stacks, regardless of whether they are formed by the greedy strategy or not. The only requirement is that the stack formation process obeys the basic rule given in the problem, which is that you can only place a smaller number on top of a larger number. This generality arises because we haven't used any rules related to the greedy strategy when justifying this observation. For the example sequence given in the problem, let us consider two different end results of stacks made from this sequence. The first example is what we already saw, stacks formed by the greedy strategy, which gives total stack number of 4. The second example is just arbitrary stacks which are not formed by the greedy strategy, but only obeying the basic rule of the problem, having total stack number of 5. If we consider one of the longest increasing subsequences, 3, 5, 6, 8, notice that for arbitrary process, now the subsequence does not follow the nice left to right direction, but you can see that each term of the subsequence still belongs to a different stack. Therefore, the inequality relation from observation number 2, which is that the number of stacks is always greater than or equal to L of x prime, the length of the longest increasing subsequence, also holds for any stacks formed by the basic rule. That is, this L of x prime acts as a lower bound for total number of stacks. Whatever strategy you use, the number of stacks cannot have values lower than L of x prime. However, from problem B, we found out that the greedy strategy gives the number of stacks that is the same as the length of the longest increasing subsequence. This is because of the first observation, stating the existence of an increasing subsequence which contains at least one entry from each stack, resulting in the length of such subsequence being greater than or equal to the total number of stacks. Unlike the second observation, this first observation requires the greedy strategy because we use the rule of the greedy strategy such as x jumping over some y only if y is less than x. So to summarize all of these, generally speaking, that is, using any strategies under the basic rule, we obtain the number of stacks greater than or equal to the length of the longest increasing subsequence. Using the greedy strategy, we obtain the number of stacks that is exactly the length of the longest increasing subsequence. Therefore, the greedy strategy gives the minimum possible number of stacks. Problem D. Find two sequences that give the same end result of stacks after using the greedy strategy. As for sequences with two terms, we don't get the desired result because sequences 1, 2 and 2, 1 give different end results of stacks. However, if we take a look at sequences with three terms, we can easily find out that sequences 2, 1, 3 and 2, 3, 1 give us the same end result. And the final problem, problem E, show that not every sequence of legal stacks is obtainable by using the greedy strategy. Here, legal stack means numbers increase from top to bottom. Given a sequence of legal stacks along a line, how will you decide if it arises as the result of using the greedy strategy on some sequence of numbers? The key here is to recall the property we proved in problem A, which is that if we use the greedy strategy, the top numbers on the stacks increase from left to right. Therefore, we can provide counterexamples asking the problem in the following way. We construct a sequence of legal stacks, that is, numbers increasing from top to bottom, but in a way that the top numbers of those stacks do not increase from left to right. For example, 2 followed by 1, 2 followed by 1, 3, 2, 3 followed by 1, 4, etc. cannot be obtained by the greedy strategy. Also, this property from problem A can help us solve the next part of the problem. Given a sequence of legal stacks, can we say that there exists some sequence of number resulting in those legal stacks by the greedy strategy? Well, let's get back to the result of problem A and make a guess that is essentially the reverse statement of problem A. If the top numbers on the given sequence of legal stacks increase from left to right, then perhaps it is always the result of the greedy strategy on some sequence of numbers. To prove this guess, let us consider the sequence of legal stacks as shown in the figure. The numbers in the first stack are denoted as x1, 1, x1, 2, etc. And since this is a legal stack, the number increases from top to bottom. The numbers in the second legal stack are denoted as x2, 1, x2, 2, and so on. And the same rule applies to the rest of the stacks. The top numbers of these legal stacks are also in an increasing order from left to right. Then we construct the sequence as follows. Take out the top entry from the rightmost legal stack and make it the last term of the sequence. Then the remaining stacks also satisfy the legal stacks condition and the top number condition. The numbers still increase from top to bottom, and since xn, 2 is greater than the removed element xn, 1, the top numbers are still in the increasing order. Now we repeat the process. The new top number of the rightmost stacks becomes the second to last term of the sequence, and we go on and on, scanning the stacks from right to left. In the end, we have this sequence. And if we apply the greedy strategy on that sequence, it will produce the initially given legal stacks. Verifying this claim is easy, so try to do it yourselves. And with this, we are done with problem B6, hence we are done with every problem in part B of the Chennai Mathematical Institute's Bachelor of Science Entrance Exam 2025. Thank you all for watching. Please hit that like button if you enjoyed this video, and I will see you in another video.